Hi, everybody. What we're going to work through today, you can see just the title at the top of the screen. We're going to go through some properties of functions. And really, the intention of today is to, again, kind of knock off some rust, but also we're maybe going to introduce some new terminology, maybe zero in on some old theory and just make sure that we've got that nailed down, and then maybe discuss just some new notation. So, what you see on the screen, and this should line up with your handout, is we've just got a little bit of information to get down. Now, let's make sure that we don't just blindly copy down the color, but rather, we're going to make sure that we stop after each section or each sentence, each component, and just make sure that we've got that theory nailed down. So, at the very top, we should be good that we know that a function is a relationship in which one quantity depends or determines or corresponds to another. That is a partial definition for a function. It doesn't really nail down all the details. But in a general case, yeah, that would describe a function. So all we're talking about is how one thing compares to another, how one thing relates to another. Now, let's take a look at what a function consists of. That is, what are the components of a function? Well, we start out with that first bullet. We should be good that a function has a set of inputs. Now, that set of inputs is what we call the domain, and I'm hoping that that term domain is something that you've heard in the past. However, I don't know if we automatically think of our inputs as domain, but rather, quite often, we tend to think of those as our x values. Even to the point where I think you may be walking into this class kind of going, okay, domain means x's. And if you think of it that way, then we're good. I just want to keep harping on that point that really all those represent is a set of inputs. We take some information and we use it as an input. We put it into something. Now, that second bullet, we have a rule. And now, I don't think a whole lot of us use the terminology rule very often. But it is a rule in which each input determines one and only one output. We're going to come back and we're going to talk about that one and only one specifically. But again, I don't think an awful lot of us think of it as a rule, but instead we would use the terminology an equation. That I hope that we would be good, that we would start to go through and say that, well, I take a bunch of inputs and I put them into an equation. And then we do whatever that rule says. And if we take that input and we put it into that rule, then it's going to spit out an output. Now, what would we call that output? Well, that output has the name the range. However, for most of us, we think output and we're probably thinking y values. So, similar to before, if you're walking into this course and you think range means y's, then I think you've got a good grasp of it. But you're going to hear me harp on the term output. So, what we have is we have a set of inputs, we sub those into a rule, and we follow that rule, and they spit out an output. I am hoping that that process sounds an awful lot like your good old table of values from grade 9. That is, you pick an x value. Those x values get subbed into your equation. You do whatever the equation says. So for instance, maybe my equation was something like this. That means you double your input and then you add 1. And it's going to spit out a y value. Your table of values is you using the components of a function almost explicitly. You take an x, you sub it in, it spits out a y. Okay, I want to jump back up and kind of zero in on that one and only one thing. So if you follow down on the page, right below, we have that statement about one and only one. So what do we mean when we say one and only one? We just mean that each input determines exactly one output. Okay, exactly. Now, I'm hoping that we're good with that terminology, and I'm hoping that we actually get the phrase exactly one output. You see, sometimes what we do when you're younger is we give you guys these rules or we give you these ideas, and we kind of allow you to think about some ideas actually incorrectly. But it allows maybe a rule or the idea behind something to be more understood. Like, so for instance, if I was to ask you, okay, name a triangle that has two equal sides. Like, I might argue, okay, I'm not going to make you spell it, but hopefully you could name a triangle that has two equal sides. And you may come up with, hey, well, an isosceles triangle. And yes, I know you'd all spell it correctly. But then if I was to ask you, okay, well, name another triangle that has two equal sides. I'm going to bet that I would get a hesitation from a large number of you. Like there is another one? I thought isosceles was the only one that had two equal... Well, how about an equilateral? An equilateral has two equal sides. And I would have some people who would go like, no, equilateral has three equal sides. And I would go, well, if it has all three equal sides, then doesn't it have two equal sides? Now, you might view that as like a play on words or like, well, you were trying to trick me, but I wasn't. If our definition for an isosceles triangle is a triangle that has two equal sides, then we need to understand that that definition isn't correct. That really the definition would be a triangle that has exactly two equal sides, or two and only two equal sides. So hopefully that just gives you an idea of what we're talking about when we have to be very focused on our language. So when we say one and only one, then that excludes the option for anything else. There has to be exactly one answer. So in this case, exactly one output. So for instance, if we take a look at the next line, if you go through and sub in one x value, then the function creates one output. Okay, one input gives me one output. Now, we might argue, okay, well, that seems pretty straightforward. Then why are we breaking this down so much? Because the confusion could be, but different inputs can give me the same output. And that's where sometimes we can get our idea a little messed up. Because we start to go, okay, so wait a second. So if I take one x and I sub it in, I can only get one y. However, different types of x's can give me the same y? Okay, wait a second. I'm confused. Which one is which? So, I just want us to draw a quick little picture. So, up in that little space in the top right corner, what you see, we're going to put on a quick set of axes. And I'm going to follow the process of choosing an input, subbing it in, and determining an output. So, I want you to imagine that I pick an input of like 1. And so I'm going to take 1 and I'm going to sub it into my equation. And then I do whatever my rule says. When I figure out whatever that does, it's going to spit out an output. And let's say it gives me an output of 2. That's what it means to have the point 1, 2. If I chose 1 as my input, I sub it in, I follow my rule, it spits out a 2. Therefore, the point 1, 2 is on my relation or my function. Okay, well, let's say that I go and I pick a different input. Maybe I pick like -3. Okay, so I take -3 and I sub it into my rule and I do whatever it says and it spits out an output of 2. Well, then that's what it means to have the point -3, 2. Are we okay with that as a function? And our response should be yes. That I have two different inputs and they gave me the same output. So I have points across from each other. And we should be totally fine to have points across from each other because, like last year, one of your big focuses was dealing with a parabola. Well, parabolas almost everywhere have points across from each other. Okay, let's say we go back to the beginning though, and I choose an input this time of 1. And now I sub that 1 into my function and I do whatever it says. And this time it spits out a value of like -4. Well, now we should have a problem. That I actually have points that are above each other. One time when I subbed x in, it gave me 2. The other time I subbed in 1, it gave me 2. The next time I subbed in 1, it gave me -4. So 1 gave me 2 and -4. Okay, wait a second, I have a problem. My input of 1 gave me 2 different outputs. Okay, I can't have that. Now, some of you guys know that you can't have that because you learned in the past about a vertical line test. And you know that if you scan across with a vertical line, if that vertical line ever hits your graph in more than one spot, then it is not a function. It's actually breaking the one and only one rule. And so what we see in that last statement then is we can have points that are across from each other. We have no problem with that. But can you please underline? But we can never have points that are above each other. It doesn't mean that our graphs can't give us points that are above each other. It just means that if they do, it's not a function. It's just a relation. Okay, we spend an awful lot of time in grade 10, grade 11, talking about the importance of functions. You're sitting in a class called functions. You will probably enroll, potentially enroll in a class next year called advanced functions. We spend all this time being able to identify a function, but we don't always talk about, but why do we care? So let's just look at one example. Okay, so what you see on top then is just kind of us summing up a little bit or going back and maybe revisiting the point of today, us discussing a function. So a function is a rule that generates a value with respect to a variable. We should be good with that. So I went back and just kind of threw up a good old grade 9 function. There's your y equals 2x plus 1. Notice if I pick an x and I sub it into that equation tells me to double it, then add 1. And I'm going to get 1 output. The biggest issue, and the whole reason I want you to write this, is to underline the next part in that next statement. That the value of a function is the y value at a specific x value. That there would be a lot of times where if I gave you a point, so let's imagine that I just went and I subbed in an x value of 4. Then if I sub in an x value of 4 and I double it and I add 1, that's going to give me a y value of 9. We know graphically that would give us the point 49. Well, if I gave you the point 49 and I asked you, hey, so what's the value of the function? We don't want our response to mean well, which number do you want? Do you want the 4 or do you want the 9? Oh, or do you want both, 4, 9? All of those reactions are bad. The value of the function is 9. That's its value when x equals 4. So if we can drive home the value of the function is the y value, then I think that's going to solve an awful lot of the struggles that we may encounter coming up. Okay, let's jump into the next part of that page. What I've put on this page is something that I think you're going to want to pause at some point just to give yourself a chance to get all of this down. So I might recommend to you, pause it now, get down what you see on the screen, and then I want to come back and maybe talk about some of the parts to this. Okay, so let's pause the video now. Okay, we're back. So the overlying question, how can you tell if a relation is a function? So we clearly have some sort of relationship where one thing compares to another, but how can I tell if it's a special type of relation, the function? Well, we're going to encounter being given functions in various forms. So what you have listed in red are the various forms that you could see a function or a relation. You could be given ordered pairs, and then in green you just see or coordinates, however you want to think about it. You could be given the equation to that function or relation, or you could be given the graph of it. Okay, I want to tackle this backwards. So let's start on number 3, the graph. Most of us should be good coming out of grade 10 that if we're given a graph to a function, we can just use the vertical line test to determine whether it's a function or not. So the question that we're basically answering is what you see in green. Can a vertical line intersect the graph at more than one point? If you can answer that question, yes, it can, then we know it's not a function. No, it can't, then it is a function. But the green becomes the question that you basically want to ask yourself. So for most of us graphically, that's probably going to be the easiest way to determine whether something's a function. Okay, now I want you to take a look at number 2. If you're given the equation to the function, I'm going to argue that I think this might be the most difficult way to determine whether something is a function or not. And what I've put in blue is the question you want to ask yourself. That if you can answer that question, then you have your answer as to whether it's a function or not. Can an x value give more than one y value? And you notice you're going to get the same sort of response. That if your answer is yes to that, then your follow-up is no, it's not a function. But if your answer is no to that when I sub in one x value, I will only ever get one y value, then we have a function. That question you see in blue, that is our one and only one, just almost written explicitly. Okay, I might argue that the second easiest way for us to be able to determine whether something's a function is if I give you a set of coordinates. If you have a list of ordered pairs, then really all we're doing is we're just scanning over all those coordinates. And we're just checking to ensure that one x value only ever has one y value. That is, do we have a couple points that have the same x values, yet have different y values? Okay, we're going to challenge all of that. But what I want to do is I want to kind of spend time on that number 2 situation. I think 1 and 3 are so simple, I don't even think we have to review that. You have enough in your note to be able to do it on your own. What I want to do is I want to kind of jump in specifically to that second situation. What if I give you the equation to a relation? Can we determine whether that relation is a function or not just from the equation? Okay, let's jump in and go.